So this is actually like our meeting number 4. I'm going just to explain the rectangular and polar in the phasors and how to move between them and when should we use each of them. So first, for the rectangular one, this is x plus jy. This is the rectangular form of the phasor. If you want to move to the polar, so as we know, like the polar is magnitude and angle, right? Usually in degrees. Magnitude is the square root of x squared plus y squared. And as angle, you can call it like tan inverse or arctan y over x. Now we moved from rect to polar. If you want to move from the polar to the rectangular form, let's put like one as a angle theta. Now you have it in polar and you want to go to the rect. So as a real, so it's a cosine theta plus j. This is the part of the like the real, similar to the x, and j a sine theta. This is, you know, similar to y. And you can actually draw this in a phasor. This is the real and this is the imaginary. So for the x and y, this is, let's say, the x, and this is the y. This is actually your phasor. X is the real, y is the imaginary. Or it's like this one is a, and the angle here is theta in polar. Okay? When should we use the rect or rectangular form and polar? Usually we use the rectangular form if you want to add or subtract the phasors. Polar if you want to multiply or divide the number, the complex number, or the phasors. And I provided one example. Let me repeat it. So it's x1 plus jy1, and you want to add x2 plus jy2. Okay? Or of course subtract, like it doesn't matter, add or subtract. So the total is you add the real plus the real, and then plus j, and you add the imaginary, sorry, y1 plus y2. If it's
Mohammed,
like you have negative sign, you can put the negative sign here. Okay?
Mohammed, one
Yes,
question.
there is a question. Yes, please, yeah.
The first term is the real part. The first term of the rectangular number is the real part, and the second one is the reactive, the resistance. It's not the opposite. This is the admittance, and the second one is the reactance. It should be changed, isn't it?
Which one? Sorry, like
It's when you say y is the invert, the invert of the resistance, right? This should be the real part of the, or not?
Okay, no. Yeah, I put like x and y here. It's just terms, but I can put,
Okay.
let me, because now, yes, now it seems we mix between reactance and admittance. Let's call it like A and B.
Yes, and no worries. Just to
yeah,
clarify the convention that you're using, that's enough.
yes,
Because usually it's common we use y as a admittance.
admittance.
Yes,
Yes,
and
yes,
the
I agree.
x as a
And
reactance.
X reactance, yes. I completely agree with you. Even for this reason, we use J for the imaginary, not to mix it with the current. So I agree with you, like only in circuits we use J for the complex number. By the way, like all the mathematical forms, you will see I instead of J, but the reason it's exactly as you said, it's like the reason for using X and Y, because I use the X axis and Y axis. So sometimes in math, actually, like we use the X, not for the reactance for the circuits, but we use it for the X axis and Y axis. And yeah, so that's the reason we, maybe it makes it between, and it made like some confusion, but I mean by X and Y, any letter, let's say A and B. So you will put here like A squared and B squared, and here it's like B over A instead of X and Y. X is not the reactance, Y is not the admittance. Okay, here A is A, like it's just a letter. Similar to here, like, you know, like it's A's or and B's. So for example, like it's not the reactance, not the admittance. Okay, to fix all of this confusion. Okay, let's do the polar multiplication or division. So for multiplication, A1 angle theta 1 times A2 theta 2, you multiply A times A1 times A2, and you add theta 1 plus, so you add the angles actually in multiplication, and you multiply the magnitudes. For the division, let's say if you have A1 angle theta 1 divided by A2 angle theta 2, then the answer is you divide the magnitude and you subtract the angles. The one here, it goes into a negative with a negative sign in the numerator. Okay. Any question? And try to do it. You have to make sure that using your calculator, you can use it for this complex number. As I said, we started to have this calculator with the complex numbers once we started the AC circuit, I believe second grade in the electrical engineering schools. Okay. Any question or comment for polar and rectangular? In the exam, you don't have to show all the steps, but definitely if you feel comfortable to include them, that's okay. As long as you do it in a reasonable time, not like to waste time. But for in my solutions answers to the past exams, you will find that I put some hints, and sometimes I put like more steps and comments. In the exams, you don't have to show everything as long as you are doing it correct. If you are afraid or you want to review at the end, of course, feel free to add as much as you can within the time for each question. Each question in the exam is about 35 minutes. Make sure to solve, and I'm talking not the exams, but even in our assignments, assignment 1, assignment 2, okay, midterm, each question is about 35 minutes. Don't take more than 35 minutes. Definitely at the beginning, you may use more, but by the time you shouldn't, or you should reach to maybe like 30, 32 minutes, that's okay. Up to 35, you are fine. Okay. If you don't have, okay. Do we have any question? Okay, no questions. Let's start by start with our outline. As I said, meeting number 4 today. Let's go to our schedule. So meeting number 4, we should finish the transformer. Okay, and I still remember we have one question in the assignment number 1. Let's solve it for the transformer, the third question in assignment 1. And so finish, hopefully we finish the transformers, module number 4, okay? As we do every module, I'm going to solve one question. I believe for the transformer, it will be enough because as you will see now, usually the problem for the transformer is standard. it's something, you know, like default problem. Okay. And you know, like usually I recommend to start the exam with this problem, the transformer problem. So it's usually the easiest and straightforward. Okay. Any question? Maybe I can stop the video for the streaming, and I can start the transformer one, like the module, and let me make it in the full screen to make it better for you. Okay. Transformers, module number 4. As you see, we still have one module to until the exam, the midterm. And we already finished, you know, like the magnetic circuits and power and three-phase. So feel free to check the exams for both, like magnetic circuits and power and three-phase circuits. Today, I'm going to upload one full exam with the answers. Okay. So you will have many questions for the three-phase, 2-watt meter method, and transformers, of course. So for this one, the main part is we should know the basics of the transformers, or like basic knowledge for the transformers. And mainly we are going to do some kind of tests to know the parameters of the transformers. So we have 2 tests. We call it like open circuits and short circuits, or OC and SC. 2 tests to get the main transformer parameters. We will discuss it now. We will start first by the equivalent circuit, and then we will go to the approximate. This is the second one, approximate equivalent circuit, which we usually use in the exam. Okay. We should understand each component of the equivalent circuit and make sure that we can solve some kind of like not just the open circuit test and short circuit test in the exam, but do some kind of other parameters, or get other parameters such as the voltage regulation and efficiency. We start very like in a, you know, steps. The first one is the basics and the principles. We will start with the ideal transformer. Then, after finishing the ideal transformer, we will jump to the real transformer. This is actually what we will use. In the assignment one, you will see that I put one problem or a part, like part B. It was regarding the ideal transformer, just to make sure that you know the concepts. In the exam, most of the problems are the real transformers. Okay. Then, as I said, at the end, we get the parameters or the approximate equivalent circuit of the transformer, and we are going to get 2 more parameters, VR or voltage regulation and efficiency for the transformer. Okay. Any question, comments? I can hear something, but I
guess there is someone
please,
with
yeah,
the microphone.
Oh, yeah. Hey. Okay. So let's start the transformer, the basics and the principles. This is the about or regarding the history. Do we have any question? Because I can see some, okay, I can hear some noises.
I guess it's, yeah.
Oh, okay. Okay, very good. So for the history of the transformer, I would say that transformer is one of the most important equipment in the power systems. First, like the practical one started very early, like 1885. And, you know, like it was like, I can say like the turning point to move from DC, because the electricity started as a DC, to AC. And there was like, as you know, like it's the war between the AC and the DC at that time. So transformer actually like helped the AC side. And as you know that the transformer, we have actually one of the knowledge problem why the transformer cannot work with the DC. Okay. One thing you can notice here that the core of the transformer, this is the core of the transformer, okay? And you can see the windings here and the other sides, the two sides. And the core of the transformer is not one bulk, but it's laminations. I mean by laminations, it's like a very thin metal that is connected to each other through a certain or like insulation between them. And you can see that they are trying to push all the laminations to be one block. We will know the reason for this, okay? So this is the main history points that I said in more details. So first, the power distribution in the United States started with the DC 120. Okay, of course, Thomas Edison, and mainly was like for lighting, 1882. The main issue, they found that many, of course, people started to use electricity. So with the very large currents, okay, we started to see low voltage, like voltage drop, okay? Especially, of course, if you have like very large currents, which means like significant amount of power. It's also not just the voltage drop due to the high current, but even making losses, I square R for the DC. There is no X at that time, like, or with the DC, it means you don't have any inductance or capacitance. It's just the resistance. Due to this resistance and high current, I square R is very, very large. So they couldn't go very far from the generation station, the DC generation station. It was within a certain, you know, location or certain length or distance from the generation station, then you will find a lot, like very large voltage drop and losses. Okay. Of course, the power station is located in the central, and it was helping, I believe, it New York and other cities, like few blocks in the city, not the entire city, due to this problem. After having the transformer, and we will know the reason, this transformer was able to eliminate this with the AC. With the AC, we will solve actually one of the solved problem. We can step up the voltage, we can increase the voltage. Okay, if you increase the voltage for the same power, it means you reduce the current, make the voltage drop is lower, losses is lower. So the solution was to transmit the power at higher voltage, which was difficult for DC because the transformers, they do not work with the DC system. Okay. Any question in the history?
Would this history probably could be asked as a theory question? Have you ever seen it?
No, like the only question for the theory or the knowledge question is regarding the DC, why it doesn't work with the DC. So it's somehow related to the history and the main reason why the transformer was invented but it's not directly to the history. Like they don't put this, or they don't ask for the history, of course. Yeah. Okay. So for the construction, we have two main constructions for the transformers. And usually they don't ask for this in the exam, but I put them for a reason. So practically, you will see that most of the practical transformers are in the shell form. What is the shell form? This is, this is the shell form. So you have three legs. Both the primary and secondary winding at the middle leg of the transformer. We have something called the core form, which is the simplest, and we will use it here in the course. And any textbook, they will use this. They call it like the core, right? The core. You have the primary and secondary, two windings in the transformer. Okay. Sometimes we call it P for primary or 1, secondary or 2. Okay. This is the core, just one core. Okay. And two windings, both like at each of the legs, we can say, or limb. Here we have 3 limbs, and the middle one includes both the primary and secondary. This one is more practical, but we are not going to, use a lot in our, because we need like a simple one. So for simplicity, we will use this. But practically, this one is more. You can see it more in real life. Okay, and actually, you can see 3 phases. So 3 phases, like like A here, B, and C. Okay, this is more practical, and they put like the primary and secondary with the same leg of the core. Okay, and there is a reason actually for this. They want to reduce the leakage because both the flux flow directly from the primary to the secondary, so there is no any leakage compared to the one if you put like 2 here. So you have some leakage here, leakage there, and then you have the one in between, but you have more leakage for the core. Here we have less leakage. Okay, all the flux going from the primary, it's already passing through the secondary. In reality, we usually, let's say this is the leg of the transformer. We put the one with the winding for the low voltage first, and then the one for the high voltage after it. Okay, so the one with the low voltage is closer to the core. The one with the high voltage is out. So they both actually on like, or the high voltage on top of the low voltage winding. Okay. And maybe like the reason for this, like, or the main reason for this, if there is like a short circuit with due to like the insulation problem, it will be, and the core already like grounded. So it will be like low voltage to the ground, not like high voltage to the ground. So it's like less severe. Okay. And regarding the eliminations here, we are going to explain it more. But as I said in the beginning of the, like the first one during the history, we made this as sheets, very thin sheets, okay, laminated in the direction of the flux. So this is the direction of the flux, right? Like let's say the flux is moving here and there. So the laminations are in the direction of the flux. Okay, they have a certain maybe like insulation between them. Some of the materials, they call it like mica, for example. This is a kind of material to put in between the laminations. So they are not connected electrically, but of course, during the magnetic field or the flux, they will flow inside it. There is no problem. We try to minimize something called the eddy current. Okay. What is the eddy current? If you have a flux in this direction, phi, similar to the, like the conductor with a current carrying, you have a flux. If you have a current flow, then you will have a flux. The flux is perpendicular actually on the current. If this is the up and down here, or like the from bottom to up, the current, the flux flow in perpendicular to the current. And similar to this, if you have a flux and inside this metal, the currents will flow in like perpendicular to the flux. This current is moving randomly because it's like a block of metal. Make a lot of losses, I square R. The R is the resistance actually of this core. So to eliminate this, we can make the core into a small sheets, small laminations, and make insulation between them. So the current will be very small, right? It will not see a bulk of metal flowing from point to another point. It will see a very small sheets or laminations. This one is actually to minimize this current. We call it like eddy current. To minimize, but not to completely eliminate this current, because it's impossible to be eliminated. You will have a very small current here, but not zero. The current here, we call it eddy current. Eddy because they flow in, like not like if you have a conductor, you know that the current will flow from point A to B or B to A. But if you have a block of metal, then the currents will not have a certain direction. They can flow in eddy kind of like paths. This is the reason we call it like eddy current. Okay, it's like a random current. Like let's say, like it's randomly flowing from a point to another. How to minimize this eddy current and the losses? By making it laminations, and we put a kind of insulation between each of them. Okay, we will discuss later about the eddy current, but I found it here, so I just wanted to make some notes before we go forward. Any comment? As I said, we have two windings. In this course and exam of the PO, we have only like single phase transformer and two winding transformer. One primary or one, and another one secondary or two. In reality, you can see, of course, three-phase transformers. In reality, you can have more than two winding transformers. You can have three winding transformers, for example. Okay. So the applications of the transformers, we discussed it during the history, the main applications of the transformer, but there are different applications, not just the high power, which we will discuss in the next slide, but even in the electronics to make like isolation between two systems. Okay, because for the transformer, as we see here, they are not electrically connected. There is a kind of isolation between the two circuits here as electrical. There is no conductor from primary to secondary. So this one can be like isolation. In the three-phase, you can actually move between delta to star. It's good for protection. So moving from delta to star, you can actually eliminate the fault or reduce the fault current. You can use, and this is very common in the distribution systems, for voltage regulation. So not just to step up or step down, but to slightly adjust the mismatch between voltages. To explain on this, like, because this is like one of the good point distribution systems. So sometimes, let's say you have a voltage and it's like 120 volt. Usually in the power systems, we define the voltage, define the system or the systems by the voltages. So we can say 500 kV system, kV, kilovolt system, 230 kV, okay, 36 for like kV for the distribution or so.
Can I ask a question at this point here?
Yes, please, yeah.
What is the range for that dictates if something is a system is low voltage, medium voltage, or high voltage?
This one, like this question is very, let's say, tricky because it depends on the company. For example, if you work for the system operator, they are working on the 500, 230, and 115 kV. So when they see like something blue, like the 50 kV, they will say it's a low voltage. But if you are working on distribution systems, so they see like 480 volt, they will see the 50 kV as a high voltage. So they will call it actually within their company as the high voltage side. So it depends on the, there is no standard, to be honest. And however, some people, they put kind of, you know, like boundaries. So they said anything above 1 kV, it's high voltage. Below this one, like it's low voltage, okay? However, this one, I completely like disagree. It depends on the, you know, the system. You are talking about the transmission. So this is the, in Ontario at least, this is 500, 230. They are the backbone of the system. 115 is a kind of sub-transmission, we call them, systems, okay? Lower than this, then it means you reach to the distribution level. But again, it depends on the situation and the company, not the, you know, like real design definitions for the voltage. Sometimes with the voltages, we have here 500, but sometimes can reach to 750 kV. Other voltages in this range, 345 in United States. So we have different voltage levels, and it depends on the, you know, the system you are in, the standard in this system. And one thing is like the geographical areas. You can go to very, very high voltage if you have very long transmission system. Because the larger voltage you can go, it's the less voltage drop and losses, as we said. So this question is you know, like very, or I don't have a clear answer for it. It's a kind of like a gray, and it depends on the situation. But if you, let's say you are going to a certain company, and you know it's a distribution company, so you cannot use the 500 and 230 kV with them, because this one for them is very, very high voltage. You can, like 36 actually kV for them, it's a high voltage too. But maybe like 480 or 120 volt, then it's like the low voltage. Okay. Hopefully I answer this question, but okay. One of the applications, and it's a good applications for distribution system, let's say. This one is the voltage regulation transformers. We have some kind of transformers. And if you have a voltage of like, you know, at home, or maybe like it's not at home, maybe at factory or something, it's 480. This voltage, you need to have this certain voltage in your factory, for example, 480 volt, because all the your motors, your systems, you know, depend on this voltage. Okay, so how, like during the system or inside the system, the voltage can reach to 485 volt because of the changes in the voltage here in the transmission. So for this reason, we put one transformer, it's like 480 volt to 480 volt, but you have some taps here, then you can change in case you have this voltage reach it to 485, then you can try to change the number of turns slightly to make this at 480, to make your load see the 480. And we call this kind of transformers, and we have them here in Ontario, the voltage regulation transformers. So they are not changing the voltage much, slightly change the voltage, and they have something called the taps. We will discuss it later. So the taps or the tapping of the transformer, we can change to make this voltage constant, even with the changes here in the transmission system. In the transmission system, we try to make the voltage as defined, the 500, we try kV, we try to keep it at 500 kV, but definitely due to the changes and the dynamic of the system, you will never see something at exactly 500. You will find 501, 502, 503, or 496, but within a certain range, of course. Okay. An instrumentation transformer, it's another application, very important. We use it, for example, for the power system protection, something called like potential transformers, current transformers, PT and CT, to measure the voltage and the current in the high voltage levels. So for the current transformer, we try to make it in series to get the current, okay, or to measure the current. And the CT, we put it like in parallel to measure the voltage, okay, or the PT. So we go to lower voltage. So for example, if you want to have like electronics things, so you can use lower voltage. You cannot use the 500 kV directly, right, in the electronics. And this can go to the relay, which connected to the circuit breaker for this, for example. Okay, this is just the applications of the transformer. We don't want to go deep, but just to show you that it's not just the power transformer that we are going to explain in this slide, but they have different applications. The main one was the power transformer. In, for example, Ontario's power system, we have maybe like thousands of transformers, starting from the generation up to your load. So for the generation, here we have one of the generators, okay, connected here. This is the generator. You have step-up transformer. Because the generation, you cannot go beyond, for example, like 30 kV, 35 kV, but you want to make the voltage higher. So you make it the step-up transformer, make the voltage higher. You can see for this transmission, it's like 500 kV. Then you reach close to the load system, like your distribution system. So you have something called distribution substation, and you go to lower voltage. like 69 kilovolt. Then you have another transformer because you want to decrease it on a level, right? You cannot put like from 500 to 100, but you put it like on in a level. This is the first level to step up, this to step down, and then you have another transformer to step down more to 7.2 volt. And then from the 7.2 kilovolt, sorry, 7.2 kilovolt, you can actually use, this is the one phase. If you can see, you can see here like hot 1, 2, and 3, because you have 3 phases. We take actually one of the phases, one neutral. So this is a single phase system. And then we split this single phase, reduce it to 240. Between the hot and hot, we have another neutral here. So this transformer actually is something like this. And this one is 240. Okay. If you take like between the middle here and this, then it will be 120, right? This is actually the system that we have. And I believe most of you can see this transformer close to their home. Okay. So this was to show and explain the transformer. We have the history. Yes,
I
we
have a question. Yes.
Yes, please. Yeah.
Can a substation receive 2 supplies from different power stations?
Yes, definitely. And not just one transformer.
Mhm. Well, definitely. So each transformer that steps down the voltage would have its own grounding system or network associated with it, or would they share the grounded network?
They can definitely share the ground. So if you, let's say you have a substation and you have 2 transmission lines.
Yes.
So
yes.
you have 2 transformers, and sometimes we have this is the high voltage. Let's say I'm going to use like high voltage and low voltage, but it's not like maybe this one is a medium voltage. It's not like very low voltage. And we can actually take some numbers here. Like we can take like the 500 kV and this, let's say the 69 kV. So 2 transformers, we try to, sometimes we put them in parallel, but usually we put like one breaker here. So sometimes they work in parallel, connected to each other. Sometimes we open this, but then they are connected to multiple feeders at the low voltage. And each one, they have their own breaker, of course. So the feeders here can feed different parts of the system, not just, here we put like our drawing here is very simple. It's just one line from, generation to a home, but definitely you have more homes here. You have more lines going to different areas. And this one is example of the substation. To be very clear for the name of the substation, because sometimes we call the substation that includes the transformer. In my company, for example, we don't use this. We use substation if you have only breakers, no change in the voltage level. However, it depends on your again, like maybe like the system that you are using, or the terminology that is used in each system. But I understand that in, for example, United States, sometimes they use the substation as the one that we have transformers. What we call this in Ontario, we call it like transformer station, like TS. If we have a distribution system, so we call it distribution station, okay, or DS. Substation it's used only if you have something like this, some breakers. Okay, switching, sometimes we call it switching station. Okay. Regarding the grounding, definitely they can share the grounding, and it's basically, it depends on the protection scheme too. So like it's not straightforward, especially if two transformers in parallel, it can take a lot of protection, you know, I would say like a scheme, because you can have some kind of like flow back on the transformers. So you want to make sure that they are, you know, like they are this breaker is closed, they are in parallel, but the power is going to the low voltage and not going between the high voltage to low voltage in case something happened in the system. Okay. This is, and to be clear, this is a very big top, the transformer and substation and the system in the power system or the grid. Okay, it's the main application for the transformer, but it's not the only application, as we discussed in the other parts. Okay. Hopefully I answered the question, but yeah,
Yes.
feel free.
Yes, you did. I'm actually curious. Are any of the classes offered would ever go over how to create a protection scheme, like a realistic class?
For the protection, I believe this is like a very big topic, the protection. Even I consider myself as a power system engineer, not power system protection engineer. So it's another, it's not like, of course, for the power system engineer, they must know some level of protection, but the protection itself, it's quite big a topic that require a lot of experience to be honest. And it's a very big topic. It's not just maybe, I'm not sure about, of course, if you are talking about exams in the PO or just for power system protection, but the in general, the power system protection, it's a big field that I believe even during you can start your career. Usually the people start their career as a power system protection, and then they stay in this field. You can't actually jump between power system engineer to power system protection engineer. It will, after some years of experience, it will be difficult.
Okay.
So it's like a path actually in itself. It's not just one. It's a big topic to be honest, but definitely it's interesting. And some people, they call the power system engineer, like power system protection, as a kind of art. It's like it's not just engineering, but it's like you have the flexibility to design your own and actually like apply it. So it's a very interesting topic, to be honest. And I really like to discuss things with the power system protection engineers in our company and in different companies too. So
Okay.
it's very interesting. And by the way, power system protection field can be transmission level or distribution level. So actually it depends on the level you are discussing. Sometimes we do different protection schemes in the distribution and low voltage level, as we said, than the one in the transmission, for example. So they have a certain kind of in the transmission, the protection system is to protect your device. The transmission system is very, very high cost equipment, and the protection sometimes is more advanced than the one in the distribution because it's more important equipment, right? So
I will
but
possibly email you to continue the conversation, because
yeah,
I would
yeah,
like
sure.
to learn more outside of just working in it. If there's any sort of course.
Yes, yeah, sure, yeah, yeah. I can
Thank you.
try to advise you, especially like some very important books in the
Yes,
power system protection. Yeah.
thank you.
Yeah. Feel free to email me, please. Thank you. Okay, for the fundamentals, and I believe we discussed this point about the transformer and the main points here. The first is that we have, for simplicity again, we are going to use the core form or core type. We have one iron core, okay, for the flux. Make sure that's better than the air, of course. Low magnetic resistance or reluctance, as we said in the magnetic circuit. We have one primary, one secondary, primary and secondary, voltage and current. NP is the number of turns of the primary. For the secondary, we have here the number of turns of the secondary, NS. Currents, IP is the primary current, IS is the secondary current. P, voltage, VP, and VS, voltage at the primary side and secondaries. Okay, simply we can draw the transformer as this symbol. Okay, sometimes in the power systems you will see two circles. That's fine too. Okay, sometimes it's like this. Okay, so you have different symbols for the transformer, or the schematic symbol, as we said here. Okay, but it's simply to eliminate the core. We don't want every time to draw the core, so it's just remove the core, and we put this one to say we have a core, like the two lines here. Okay, for the dots, we will discuss it later. The reason for having these dots. Okay. So main equations that we are going to use for the primary and secondary. First one is the voltage. For the voltage, we have NP here, NS, VP, and VS. As you increase the number of turns, of course, you will increase the voltage related to it. So it's what we call it like proportional with the NP and the voltage in the primary, similar for the secondary. So the ratio between voltage in the primary to the secondary equals to the number of turns of the primary to the secondary. We call A, and this is important, turns ratio. Turns ratio. Here I put it in the time domain, then in phasor. In phasor, you will see there is no function. It's not in function in time, and I'm using the, big letters. Okay. For the current, it's the opposite. So for the current, if I said I primary to I secondary, it's equal to N secondary over N primary. Okay. There is like inverse to the voltage. The reason for that is we are talking here about the ideal transformer. For the transformer V, the power, let's say we have a transformer here, the power in equals to the power out. This is ideal transformer. This is the power at the primary, the power at the secondary. What is the power? It's the voltage times the current. Voltage times the current. They are equal, as we said, the power in the primary and the power equals to the power in the secondary. Ideal transformer, no losses. So voltage and current times the voltage and current in the primary equal to the voltage times the current in the secondary. So VP over VS equals to IS over IP. You can see that they are reversed, right? And equals to the NP over NS equals to the A, the number of turns, or the turns ratio. A is the turns ratio, okay, of the transformer. So this equation is important. Voltage in the primary over voltage to the secondary equals to the NP over NS, which is the A turns ratio, which is, inverse to the voltage current in the primary over current of the secondary. Okay. Any questions so far? Okay, let's go next. I cannot. Okay, I have a problem with this. Okay, now it's cleared. Next. Okay, I believe we reached to 3. Sorry, time is now 7:12, so we can have a quick break and then for 10 minutes. And let's continue. Now we have, as you said, we are discussing the ideal transformer. We are doing the something now very important for the ideal transformer. We are going to expand it to the real transformer. So when we have, let's assume that we have our transformer here, primary and secondary. And let's say we put on the secondary a load called the impedance ZL. You have the voltage across the impedance VS. This is the V secondary, voltage, current, I secondary. So ZL actually is, you can get the values for the impedance, this impedance of this load as the voltage over the current. Of course, all in phasors, right? The voltage and currents are in phasors. Even the angle, like the impedance will be like magnitude and angle or real plus J imaginary. Okay, it's a complex number, phasor. Okay, we have this impedance in the secondary. For the circuits, to solve this this kind of circuits, it will be impossible because you have a transformer here. It's something that electrically disconnecting the two circuits. So what I'm going to do now is to move this impedance to this side by saying like moving. I'm not actually moving it, but I want to see the impact of this impedance on the primary side here. And then the equivalent circuit will be something like me move this. Yes. Then the equivalent circuit will be something like as if the impedance is here, and that's it, like one circuit, and ignore the secondary. And this will be the ZL, but I'm going to call it like prime. Okay. So what is for the ZL prime, what is the value? It depends on the current and voltage. It's a voltage actually over the current. So it's the voltage V in the primary, of course, voltage in the primary over the current in the primary. I want to relate the impedance ZL to ZL prime. I can use the relationships that we used in the transformer, the ideal transformer, that the impedance in the primary over the impedance of the secondary equal the NP over NS equals to something called the turns ratio A. So turns ratio A, I can say VP equals the VS times A or A VS. And similarly, I can use that the current, the IP equals to IS over A. The current relationship is reversed to the voltage. Now, I have the VP and IP. Can I put them here? Substitute with the VP and IP. It's by AVS and IS over IA. At the end, it will be A squared VS over IS. VS over IS is actually the impedance ZL. So you can say the impedance seen in the primary, this is the impedance ZL, seen for the primary equals to the A squared ZL. This is actually very, very important. And we are going to use this a lot. We call this as referring, and it means you moved something from one side of the transformer to the other side. You moved maybe resistance, reactance, you move this impedance to there. So at the end, it will be something like this, A squared Z. Let's say here you have V and I. You will have the same V and I. It will be a simple circuit now. But the change is in the value of the impedance itself. Okay, and we call this one is referring. Let's say you have impedance in the primary and you want to move it to the secondary. Can we do this? Yes, definitely. It will be, this is the secondary now, but this impedance will be, let's say it's called Z. It will be Z over A squared, over A squared. Instead of multiplying by A squared, now you divide by A squared. So any impedance in this side going to this, you multiply by A squared. Anything in the primary, move to the secondary, you divide by A squared. Okay? So you can do referring to primary or to secondary. From the secondary to the primary or from the primary to the secondary side. Okay?
Sorry, a question.
Yes,
Maybe
please.
it's a basic question, but why should we, for example, on the primary side, why should we use this formula? Because we know normally in practice, we know the voltage of primary, we can easily measure the current of primary and just calculate the impedance. Why should
Yes.
we use this formula?
Yeah, this is a good question, a very good question, actually, because we will see now on the tests, the open circuit test and the short circuit test, we are going to change the transformer from one side, okay, to other side. For example, the open circuit test, we will do it in one side. The short circuit test, we are going to do it on the other side. So we have to know how to move from one to another. In the exam, sometimes they change. So they will give you some numbers and then they will ask you, okay, do it on a certain side. So you have to be able to move between the sides from to secondary to primary or primary to secondary. So you will be able to, and in reality, secondary, yes, can be load, or sometimes it's the generation and you are doing a step up. So it depends where is the high voltage and the low voltage. Here I call it primary and secondary, but in reality it will be like high voltage and the low voltage or something like this. Sometimes we call it high tension and the low tension for the voltage. Okay. But this is a good question and we will see it in the exams. So it's like for theoretically, and in reality for the open circuit test and the short circuit test. Okay. Dot convention, I told you about, you saw some of the dot conventions there. It's, to be honest, it's not in the exam, but it's very, very important in practical life. And even we will see it later in some of the parts and the proofs later in the transformer. So for this reason, I included it here separately. And it's easy. You have some like two, as you can see, two dots or one dot at each winding. You can see it in different locations sometimes, but it's one dot per winding. What are those dots and what are the main you know, like problem regarding this, like dots, what they do in the transformer? You can see it actually in the nameplate of the transformer. If you see like a real transformer, you will find the dots and the windings, the connections of the windings in the nameplate of the transformer. So dots for the voltage, You can have a voltage like this, sine waveform. You want to know the voltage in the secondary. Is it in phase or out of phase? Okay. To do this, we assign the same, if you assign the same sign with the with the dot, positive here, okay, then you will have a positive relationship between the voltages. They are in phase, like this and this. If, let's say you have here positive, but you have here negative, then it means one positive, one negative, you have a negative sign. Here you have a positive, here you have a negative, then you have a negative sign in the voltage, negative sign here. If you have positive and positive, then again, it's positive. If you have negative and negative, then it's the relationship in positive, right? Because they cancel each other. So if you have the same polarity with the dot, then for the voltages, then you are fine. You are in the positive. If they are opposite, like this and this, then you will have a negative sign. Okay. This is for the voltage. How about the current? Because the current is exactly the same to the voltage, but instead of saying polarity of the voltage, I'm going to say direction of the current. Okay, instead of positive, negative, now you have direction from to. Okay, you have two dots, two black dots. If that one of the current is entering and the second one is leaving, you have two dots here. If one current is entering, one is leaving, then this is positive relationship between the currents. If both are entering or both are leaving the dots, then you will have negative sign. Look at the first one. You have this one is entering. This one is entering. Then you have a both are entering, right? So now you have a negative sign. One is entering. The second is leaving. Then you have a positive for the current. This one, look, this one is tricky. Okay, this one is entering. This one is not entering. It's actually, look at the other side, it's leaving the dot. Leaving, I'm looking at the dot and then the next terminal. This one is leaving. This one is entering. Okay, you have positive. This one is entering. This one, go to the other side, is actually entering. Then you have a negative sign. The main idea here is we have the dot convention for the transformers. They actually help for the polarity of the voltage and direction of the current to know what you are expecting on the other side of the transformer. If you have positive, what will you see positive or negative in the for both current and voltage? We call it for voltage as a polarity, positive and negative. For the current, it is direction from and to. Okay. Check.
I have a question.
Yes, please. Yeah.
Does this have any similarity with circuit analysis? The direction of the current, deciding the sign of the value of the current or the voltage?
It's really depending, because now when I said something like we have winding 1 and 2, I didn't say the flow of the power from 1 to 2 or 2 to 1. Maybe it's a step up or step down transformer. So I don't know the flow of the power. But the dot convention is going to give you idea if we have a voltage like this, positive, for example, what should I expect from here? It's actually in the nameplate of the transformer to help the people in the connection of their system. Otherwise, what will happen? It's not a big deal, but you will have out of phase of your system, because you expect your sine waveform to be like this. It will be like this, which is okay. It's just shifted by 180 degrees. It's like opposite direction. You have a current, you are expecting the current to be in this direction, but you found it's in the opposite direction. But with the dot convention, you can actually expect the current. One thing is in the calculations, let's say you are doing your calculations, you will see like there is a negative sign. Okay, if you have like the dot convention and you have a confusion for the, or you reverse the dot convention, you will have a negative sign. For example, if you have a load here, it's a load, and the current, we expect the current is going in this direction, and this is the load. However, let's say if you assume that the current is going out from the load, you will find simply it will be the same current, but you will have a negative sign. It means it's a load, it's absorbing power, it's not generating. Okay. We call it like it's generating power in negative, right? So it's absorbing, like something like this. It's just the direction, the convention of the system that you are dealing with. Okay. Hopefully it's clear. I know the good thing we don't have this in the PO exam, but it's, you will see that we are going to indirectly using it, but in the exam I haven't seen any question regarding the dot convention, to be honest. Yeah, but I included it for a reason. We will see it later. So for this one, this part is, let's make the, again, like it's the regarding the referring, moving from primary to secondary or secondary to primary. We assume that we have ideal transformer, so the input equals to the output. There is no losses. Okay, so if you have a transformer or any system, input power equals to the output, it means like you don't have, if they are equal, the efficiency is 100%, you don't have any losses. Then let's say this is the secondary part. Okay, you can, because it's as you see, it's ideal transformer. I'm going to use the ideal relationship with the voltage and current. You substitute, you will have the same one. So power input equals to the power output. There is no losses because we are dealing with the ideal transformer up to this point. Okay. Then we provided some hints here, but okay, we have for the transformer, let's say we have one with a high number of turns and one with a low number of turns. Okay, this is voltage, let's say like primary and secondary. Current here is I primary and I secondary. Voltage, you can see the number of turns here is higher. So I know that the current, sorry, the voltage in the primary is much higher, right? Because the number of turns is higher. NP is greater than NS, you can see. Then the current in the secondary means it's higher, it's opposite, right? Like the voltage is lower, so the current is higher. We said here, the current, because the current here is higher, we are expecting that the cross-section area of this winding is larger to withstand this large current. Here we have so many turns, but the cross-section area of the conductor is smaller in the primary because the current is lower. Okay? And this is the point here. However, taking the losses here, let's say we are talking about losses now. It's not ideal anymore, but just for clarification, if you moved your losses here to this point, you will see that it's the same. Okay, I mean by the same, this is the losses in the primary, or the number one. Number one, it means primary. Number two is secondary. So I1 squared R. I square R. This is the active power losses in the primary. Using the turns ratio for the current, so I2 equals to I1 over 2. This is the losses for the secondary. You will find that look at this. So move the losses, it's the same. So you will find the same one that we got for the referring, going from the 2 or secondary to 1 to primary or 1. You have to multiply your your resistance by A squared, by the turns ratio square. It's here, which means that the losses in the primary equals to the losses of the secondary. Even if you have different resistances here, R2 is different than R1. However, when you move from one side to another, because of the referring, they are exactly the same losses. Or at least this is like a valid assumption. We assume that the resistance, when you move, the resistance in 2 in the secondary equals to A squared of the primary. And we are going to use it in the short circuit test. You will see this one. Okay. Okay, let's go next. If you don't have any question. Oh, sorry. So again, we're still in the ideal transformer, or we will move back to the ideal transformer after the part of the losses. The voltage, as you can see in the secondary, it's you divide the primary or 1 by A to get the voltage in the secondary. A is the turns ratio. You can see the angles between the primary and secondary are equal. This is only for the ideal transformer. Similar for the current. You can see the current I1 and I2, they have the same angle. Okay, which is not valid for the real transformer, for the one that you will see in the exam. Impedance seen in the primary side, it will be A squared, so you multiply your impedance by A squared. From the secondary, by A squared, the turns ratio square. If you want to move from primary to secondary, you divide by A squared, your impedance. Okay. This example is important to show some notes. It's a solved problem in our textbook regarding the single phase transformer. So you have transformer of 480, or this is the system, 480 volt, 60 hertz, and you have a load impedance. You have a real of 4, resistance of 4, and reactance positive. It means like it's inductance of 3 ohm, or reactance in 3 ohm. Connected through a transmission line, giving the impedance of the transmission line. And then you have two, let's say, two different options. The first one, you will study the losses and the voltage at the load. The second one, you are going, instead of connecting your source directly to your load through the transmission, you will have two transformers. The first one is that step 1 to 10. And then at the load, you will make 10 to 1. Step up and step down transformer. And then back to check the load, the voltage at the load and the losses. This one is very, very important example to show you that how like important is the transformer for the system. Voltage at the load, to know your voltage drop, how much the voltage drop. And losses, this is actually the importance of the AC compared to the DC. Okay. So to solve this, first you will have simple circuit, voltage 480, okay, angle 0. We assume that it's a reference. We put the impedance of the line here. We put the impedance of the load here, and you can calculate the current. Current equals to the voltage divided by the impedance. Both are in series, so this plus this. You have the current as a phasor. Then you can get the, for example, the voltage here. It's this current times this impedance, the load impedance. You will get the voltage. Then to get the losses, you will have the current, this current magnitude squared times the resistance of the transmission line. The resistance of the transmission line is this. By the way, this is a single phase system, so we don't use the x square root 3 or multiply by 3 for the power. Okay. Then what we are going to do is I'm going to add one transformer.
Sorry, a question. Sorry to interrupt.
Yes, please.
Yeah,
go
it's a
ahead.
basic question, but what would be the result if we say that the power, I mean, now for the loss, we say that current multiplied by RL. But if we multiply it by the whole impedance, what would be the result? I mean,
Oh, this one, it will be not just the power absorbed by the, because here the said the transmission line losses. So the losses only on the transmission line. That's the reason I said the I squared as a magnitude squared R. However, if you multiply by the whole,
no,
will-
I mean the whole impedance of the line. If
Oh,
now
okay.
we just use the RL, if we just use the ZL.
Yes, if you use the ZL, now it will not be just the active power losses, but it will be plus the reactive. But we cannot use the impedance magnitude. We will add like R here, and then we say maybe like this is the for the P losses, and then we make like Q loss. Let's say losses. It's absorbed, but let's say losses. I magnitude squared times the X of the transmission. It will be the active and reactive power absorbed by the transmission. If you add them, it will, like, you know, because this is real and imaginary, you cannot add them, you know, like in a scalar form. You have to put like J, because this is in a real and this is in imaginary, similar to here. We cannot add this number to this because it's a real and imaginary part. So we can separate losses in the transmission line as active power and reactive power. Reactive power is not actually losses, but we can say that it's absorbed in the transmission. Okay. Hopefully I answered this question. For the second part is you have two transformers, one here at the load side, it's a step down, one in the generator or the supply. We will write down exactly the same. Okay, this is the Z of the line, and this is the Z of the load. This one is here. Sorry, here it's 10 to 1, a step up. Here it's 1 to 10. How can I solve this circuit similar to this? First, we have two transformers. I'm going to move this impedance to the other side here. and multiplied by the a squared. This is a. We can call this a1, for example, and this one is a2. a1 is 1 over 10. This is 1 over 10. This one is 10, only 10. A2 is 10. So to move this impedance to this side, you have to multiply by a1 squared. So this drawing will be ZL, similar, but this impedance is ZL divided by 100. I multiply by a squared. A squared, it's 1 over 100. Then we still have a one transformer here. 10 to 1. And then the source. Okay. Then I'm going to move all of them out to the other side, to the source. So it will be the source. And then I will have two impedances. One, I will multiply by a2, which is 10, right? So the first one, it will return back to ZL, right? And then the other one will be, it seems I reversed this. This is 1 to 10. And this is 10 to 1. This is step up and step down. Sorry, so this one is 100. And A2 is 1 over 10. It's not 10. I'm sorry. This one, 1 over 10, because in the transmission line, in the generator, you step up, you increase your voltage. Here, 10 to 1, because at the load, you step down, you go down to the voltage. In the transmission, this is the largest. Okay. Sorry, like this one is the ZL times 100. Then when you go to this one, it will be ZL. You multiply by a squared, a2 squared, which is a2 squared is 1 over 100. It was 100 ZL. Now it will return back to ZL. What will happen to the line, Z line? Z line will be over 100. And this will be your source, 480 and angle 0. Okay. So what is the difference between this and the main one? The line, the transmission line is divided by 100. So you can do your math, you can do the calculations, get the current here, okay? Get the I squared R, get the voltage here. You will find that because the impedance of the line is reduced by 100, you will find lower losses, okay? And better voltage drop here, like the voltage in the load will not be that low. Okay. Let me show you the answer, because now I guess it looks very messy, but this is the first one. The first one is that you have your load, okay? ZL, can you see it? It's ZL here. VL, this is the voltage, and this is the transmission line, the line, and this is your source. We assume that its impedance is 0 here as like reference. The second case, you have one transformer step up and then another transformer step down. Okay, here it's 1 to 10. This is the A2, and this is 10 to 1. This is A1. A1 is 10, A2 is 1 over 10. Let's move this to the other side, multiply by A squared, and then multiply all of this 2 by A2 squared. Okay, So I can do it here. So if you move this to the other side here, it will be, let's say, Z load prime, you multiply by this A squared. So it's 100 times 4 plus J3. Then next, I'm going to move all of them to this side. Multiply by this A squared here, now is 1 over 100. The ZL will be the ZL again, because it's you multiply by 100, then you divide it by 100, it will be the same. However, this impedance will be divided by 100. Okay? If you calculate, you're doing these calculations, you will find a great reduction in voltage drop, great reduction in the losses. So you can see the steps here. They did it in the steps. The first one is multiplied by 100. Okay. The second one, you divide by 100. Better losses, or yeah, I mean like less losses, and better voltage drop. I mean less voltage drop, less losses. Better system. The idea of this example is to show you the importance of having two transformers in step up, step down at the load, step up at the generator, step down at the load. It will make the system much better performance. We are talking here about like one transmission, but you can imagine how far is the generator from your home. It's very far, thousands maybe of kilometers away. So a lot of losses and voltage drop. So that's the reason we need the transformer, not just in 2 steps, but even the step down, as we saw, maybe like in multiple levels. Okay. Let's start now the interesting part, the real transformers. So for real transformers, the first part is, this area or this part, it's regarding the real transformer and hysteresis loop. So as I said, we will use the magnetic circuit in all the machines, including the transformer, the stationary machines. You know this equation. I can write down the real one. It's minus NdP by dt, the Faraday's, and this is the Lenz from the introduction. From the magnetic circuit, the MMF equals to the phi times the reluctance equals to the N times I, number of turns times the current, equals to the H times the L. From this equation, I need this, that the flux equals to the N times I over the reluctance. And then substitute here by the flux, you will find that N dt of Ni over R. Okay, you can take this N out, so it's N squared over R and di by dt. From the inductance, we can say the N squared over the reluctance, it's something called the inductance, the coil, the reactance. Okay, dm by dt. We will discuss what is the M later. But what I want you to know from this slide, first I ignore the negative. We can put, of course, the negative sign here, but it doesn't matter because we look at the magnitude of the E. This should be the magnitude of the E. Okay, but at the end, I want you to know, once we have the flux, it turns to be inductance. Okay. For the real transformer, we will have something called the magnetization inductance. This is Lm. We will have something called, because it's a real transformer, we will have something called the core losses. Okay. Core losses. Core losses is actually two things. One is the eddy current losses that we discussed at the beginning of the laminations part, at the beginning of this module. The eddy current losses or eddy current losses. Second one of the core losses, something called the hysteresis losses. And we discussed this in the magnetic circuit. This is the hysteresis loop. And we said we start from this point and then we go increasing the current. This is with, let's say this is like the BH, okay, or MMF and the phi. You increase the current, you reach to the saturation level, then you decrease it. You will find them as some kind of like a mismatch. You have to push more current in the opposite direction, okay, to reach to zero. This is due to the magnetic domain is already aligned and they have some kind of memory. You have to use more energy to realign them, okay, or to remove this memory and realign them back to the other side, and so on. If you have a big loop here, it means a lot, you are doing a lot of energy, and this is part of the losses. We call it like losses due to hysteresis loop or hysteresis losses. The best kind of material that they have very small, hysteresis loop. Okay. And this is the definition. Okay. Second part regarding the real transformer is the leakage flux. We said when we have a flux, it means reluctance. Sorry, reactance, or L, let's say. Flux L, or you can say the X of this L. Okay. Because the definition X, the reactance is omega L, right? And omega is 2 pi times the frequency. For the real transformer, what we ignored in the ideal transformer, that we have the current in the primary. The current will make a flux to flow from the primary to the secondary. We call it the magnetization, M for magnetization flux. We ignored in the ideal transformer some kind of leakage, some flux. Not all the flux will flow inside the core. Very few lines of the flux will go outside. This is, we call it leakage. We have leakage in the primary and leakage in the secondary. Okay, and we have magnetization flow between the primary and secondary. Sometimes this is, we call it magnetization or mutual. That's okay. L is for leakage, leakage in the primary, leakage in the secondary. So we have something here called XM, okay, or LM, because as we said, any flux, it means L. And we had the definition, if you remember, it's N squared over the reluctance. This is the L. Okay. So we have L for the leakage for the primary, or XLP, and we have X for the L, okay, here, for the secondary, or L leakage for the secondary. We have 1, 2, and 3, L and X, right? 1 for the magnetization, 1 for the leakage in the primary, the other one is for the leakage in the secondary. Okay. We have some kind of losses. The first one in the primary, we have a resistance here. We always ignore this resistance. It's the resistance of the primary, or we ignore it in the ideal transformer, but we have a resistance here and resistance in the secondary too, right? RS, RP and RS. We have another resistance. We call it R of the core due to the eddy current losses and the hysteresis losses. Hysteresis losses. As we said, R, it means losses, and usually it converted to heat. If you put your hand on loaded transformer like the winding, you will find like a heat. This is because of the resistance of the winding. Resistance of the winding primary and secondary. For the core, it's heated due to the eddy current losses. Remember the eddy current losses, the current used to flow between, it's a small because we made the core of the transformer laminated, but it's still you have some kind of currents flowing inside the core. It's a small, but still you have losses. So it's not zero. You have losses also because of your material, magnetic material. It's the hysteresis losses. It's something like characteristic due to the BH curve of your, or hysteresis loop of your material. Okay. How many parameters we have now are resistance for the primary, resistance for the secondary, resistance for the core, 3 resistances. X or L in the M, L at the leakage for the primary, leakage for the secondary. We have 6 parameters, 3 resistances and 3 reactances. Okay. This is for the real transformer. If we go next, you will find them the first, this is the equivalent circuit of the transformer, or the, what we call it, like, we can call it like model. Model, it means like the equivalent circuit of the transformer, the real transformer. We have 6 parameters. Okay, can you see the 6 parameters? Yes, it's the, if you remember, the 3 resistances and 3 reactances. The first 3, resistance at the primary, resistance at the secondary, resistance at the core. X at the primary, the leakage. Here, sometimes we eliminate the L, but you know, it's because of the leakage. X at the primary, X at the secondary, and XM between, the flux between. And this is just the normal ideal transformer, and we still can use NP and NS. Okay. One question I always get is why we have this, the core resistance and magnetization as a shunt branch. Okay. First, this shunt branch, we can put it in the primary or secondary. Doesn't matter. You can put it here, you can put it there. You just do the referring. Remember the referring? You multiply by a squared or divided by a squared. It's just referring. But why it's parallel? Why it's shunt? Let's say parallel or shunt. It's the same. They have the same meaning. They are the shunt because if you have a transformer, this is your transformer. You only see that the terminals from the transformer, primary and secondary and primary. If your transformer has no loads, nothing here, open circuit, you look at the current flow, you will find the small current flowing inside your transformer. One, because of the flux in between, even if this one is open and no circuit, you will find that there is a voltage here. If you put a voltmeter, you'll find that there's a voltage because of the flux flowing in between, the flux in the mutual or magnetization. You will find that because of the flux, there is a current flow, eddy current, and hysteresis losses. So you will find heat in the core. So you will find this. You will find that there is a leakage in the primary, and there is a heat in the primary. You will not see any heat at the secondary because there is no current flow here. It's open circuit. Even if you put like a voltmeter, the voltmeter with very high resistance, so the current will not flow and no losses. So this is the reason we put this one in shunt. In shunt, it means as long as you have a source here, voltage source here, then the current will flow and you will have this a small current, yes, but still you have a current. So we put it in shunt or in parallel. It doesn't matter if it's here or there, primary or secondary, but it must be in shunt. Okay. Okay. So what is the current? The current at no load, sometimes we call it I naught. This current that it flows here is very small current. Very small current. It's just making losses at RC and the flux M, and that's it. It's small current. It's not like a big one. It will be much higher if you connect a load here and started to absorb the current, then you will absorb more and more current. But the I naught is a small current. Okay. Any questions so far? This branch, we call it the excitation branch, or sometimes we call it magnetization branch. Okay. Okay. As we said, this is the real transformer model. We are not going to use this. We are going to do some approximation. Before we do approximation, I'm going to use something very important, is the referring. Remember the referring? I'm going to refer the secondary to the primary here. And then I'm going to refer the primary to the secondary. To do both, these are the two equations, like models for primary to secondary or secondary to primary. Okay. What we use to do so is for the impedance, it's just the A squared, right? Can you see I moved from the secondary to the primary, so I multiply by A squared. You can see in the X and R here. Then I moved from primary to the secondary, so I divided by A squared. Okay. Okay. One thing is that you can see the voltage, what happened to the voltage, you multiply by A. Here you divided by A for the current. Opposite here. Here you divided the voltage and multiply the current. Okay. So the Turner's issue for the voltage, because the voltage, remember the V primary over V secondary equal A. So when you move the secondary to the primary, it's equal to A. At the primary, it's A times the voltage. So when I move, I multiply by this. The current will be opposite, right? Similar. If you want to move from the V secondary equals to the VP over A. So you divide it by A. The current will be the opposite. So you can refer from primary to secondary, secondary to primary. The two circuits. We call this equivalent circuit. Equivalent circuit or equivalent model of the transformer. This is what I explained. The first one is the winding resistance. Here we call it 1 or P for primary, 2 or S for secondary. We have R1 and R2, the copper losses, okay, or the conductor losses for the windings. We have leakage, X1 and X2. We have magnetizing reactance, XM. We have RC for hysteresis and eddy current losses, RC. I put the definitions for the eddy current. Hysteresis losses are heat, right? One, because of the current, the eddy currents in the core. One because of the magnetic domain rearrangement or aligning in the core due to, of course, each cycle for the AC. Then this is your transformer, model or equivalent circuit. To be honest, we are not going to use this model. We are going to make some approximation. Okay. To start the approximation, we said, just before we go to the next one, we said the current flow here, the no load current, we call it no load because if you don't put any load, still the current will flow, I naught. No load current is very, very small. Okay. Because no load current is small, I can move, I can show you in the one of the other, sorry, this one. I can move on the part of the primary or the secondary, this one to here, or I can move this to the other side. It doesn't matter. Like you can move this to the other side because this current is small. So at the end, the voltage drop here, due to the I naught, it doesn't like really matter. It's a kind of approximation. It will not be exact, but it's a good approximation. So you can see here what I did. I moved the one for the primary, R1 and X1, to the other side, to R1 and X1 here. Then I have real and real, sorry, and real here, and imaginary and imaginary. So you add the real plus the real and imaginary plus the imaginary. You get something called the approximate equivalent circuit. So in the exam, this is what we are going to use, the approximate equivalent circuit for all the problems. When they ask for the approximate or the equivalent circuit of the transformer, it's like this. RC XM, or you can put the JXM, R equivalent, JX equivalent. That's it. Okay. You know that R equivalent, if you are, refer to the secondary, it's R1 plus A squared R2. This is R1 and A squared R2. And X equivalent is X1 A squared plus A squared X2. Right? And this is if you are referred to the primary. Can I refer to the secondary? Definitely. You can move between both. And instead of multiplying by A squared, you are going to divide by the A squared. Okay. Here RC over A squared, XM over R squared. Okay. And the R equivalent is R2, of course, without any, and R1 over A squared. This one is, of course, X2 and plus, sorry, X1 over A squared. Okay. With X, you can put J, just not to forget that it's imaginary one. Okay. Any questions so far? One of the very, maybe like approximate equivalent circuit we are not going to use, but just in case if you are studying power system engineering, for example, you will find the equivalent circuit of the transformer can be just R and L, resistance and reactance. This is referred to the primary or refer to the secondary. Here we ignore the I naught because it's very small. Okay. So we can ignore the completely this branch completely. And the transformer equivalent circuit is just R and X. And sometimes we do like more approximation. We put it just X, the leakage. That's it. So to make very, you know, like approximate equal circuit for the transformer. We are not going to use this. This is just for your information. Let's start the main things for the transformer, the open circuit test and the short circuit test. Maybe, I don't know if we, okay, like we reach it to 4:23. I can, okay, it's 8. We can have like a short break, 5 minutes to 28, and we can continue. Okay. Here we have, we are going to start to get the 4 parameters of the approximate equivalent circuit of the transformer. Let me show you the 4 parameters first. So as we said, the equivalent circuit will be, this is the approximate equivalent circuit, but this is what we are going to use in all the problems. So you have 2 resistances, RC and R equivalent, JXM and X equivalent. Here I referred to from the secondary to the primary. So this is referred to the primary. So if you open this resistance, it's R1 plus A squared R2. This one is X1 plus A squared X2. 2, it means secondary. 1, it means primary. RC and XM, usually we put them in the primary, but definitely you can refer them to anywhere, right? Using the A squared or divided by A squared. We have to do 2 tests to get the parameters. How many parameters we have? 2. So for each test, we will get 2 of the parameters. For the open circuit test, we are going to get RC and XM. For the short circuit test, we are going to use it to get R equivalent and JX equivalent. Okay. So 2 tests, each one will get 2 parameters. Let's start the open circuit test. So for open circuit test and short circuit test, actually, we will have 3 meters: voltmeter, ammeter, and wattmeter. Wattmeter to measure the power, ammeter to measure the current, voltmeter to measure the voltage. Okay, this is your transformer. One of the side of the transformers, you put the meters, the 3 meters. The other one will be open circuit. Open circuit, or sometimes we call it no load. Open circuit or no load, no current here. I here is 0. Okay. As I said, this test is to get the RC and XM, to calculate the RC and XM. How come? How can we get, why the open circuit is getting the RC and XM? From the equivalent circuit, you have RC and JXM, and you have here R equivalent and X equivalent, or JX equivalent. This one, this part is open circuit, right? So no current will flow here. 0. So you can ignore this complete branch. You only have R, C, and JXM in parallel. You got the losses, or like the power, active power, current, and voltage. 1 point, and it's like exam note, where to put your meters. To know this, or to understand this, we know that the current during the no load is, I note, is very, very small. Okay. So usually we put our meters at the low voltage side. and the high voltage side of the transformer is the open circuit. Why the low voltage side? Remember, for the transformer, we said the part with the high voltage is low current. The area or the side for the low voltage, it has the high current. Because the current is already very small, to be able to read it or to make it easier to read it, we are going to use the low voltage, the one with the high current. So the low current during the no load, you can able to see it. This is one point. Okay. Second point. During the open circuit test, we go to V rated, to the rated voltage. We increase this once we started the test. Okay, we did this test in University of Toronto labs. So we increased the rated voltage to V rated. So it's better to do it at the low voltage side because now the voltage will be manageable, right? It will be within your, settings or like lab capability, let's say. If you put it at the high voltage side, now you need the V rated, then you have to go to higher voltage. You have to get, higher equipment to reach to this voltage. So two things, the reason we put the parameters or the meters in the low voltage side is low current. So we need high current side to be able to see the no load current, which is low. During this test, we go to the rated voltage. So we need to see, or we need to reach to this one. It will be much easier in the low voltage compared to the high voltage side. Then we do a kind of equations that you need to memorize or maybe include it in the 8 sheet. It's, you will get the Y now, the admittance, right? So it's a circuit, but you don't have to solve it every time. You only need to memorize some equations. You have two circuits, two elements, RC and JXM in parallel, and you have the power, current, and voltage. How can we calculate this? Okay, as long as you have R and X in parallel, so it's easier to use them instead of impedance because the impedance is, they are in parallel, right? So the multiplication over the addition, this is the equivalent. However, if you get 1 over the impedance, the admittance, it will be 1 over RC. So it's much easier, right? Or now you separate both of them. Here they are combined, right? But now if you have the real is 1 over RC and the imaginary is 1 over XM, and that's it. So you separate both. So it's good to use the admittance. How can they get the admittance? The admittance equals to current over the voltage, of course, in vector, or let's call it like phasors. Do I know the magnitude of the current? Yes, of course, from the ammeter. Do I know the magnitude of the voltage? Yes, from the voltmeter. Can I get the current? Yes. So this is R and C. Sorry, R and L. So the voltage, I am going to assume that's a reference, 0. The current, it's lagging. Remember, it's lagging because it's R and L, reactance or inductance, let's say. I know that the angle is negative, so I can put negative sign here. I know the power. Remember, the power equals to V magnitude I, magnitude cosine the angle. So I'm going to use this to get the current, the angle. It's cosine inverse power over VI, magnitudes, of course. And this is the equation. This equation in magnitude and the angle go to real plus J imaginary. And now if you have the real, it's 1 over RC. If you have the imaginary, it's 1 over XM. And that's it. Okay. This one is for the open circuit. I have the equations here. I will call all the voltage, current, and power from the 3 meters as OC, like for the open circuit. Magnitude is I over V. Angle is minus cosine inverse of PV over IC. Go to the imaginary, rectangular form. The real is 1 over RC. Imaginary is 1 over XM. And that's it. Okay. One thing, one point, important point is, where did I get the parameters? I told you I'm going to add the meters here at the low voltage and high voltage is open circuit. So because you are measuring the parameters here, they are referred to the low voltage. This is a very important note. When you get the RC and XM, make sure you include this one at the low voltage, okay? Because we will get R equivalent and X equivalent. If, let's say, the R equivalent and H equivalent at the high voltage, now you cannot include the circuit altogether without referring one of them to the other. To have this circuit, both must be at low voltage or at high voltage. You cannot have 2 of them at low voltage and 2 at high voltage, and you cannot do this in one circuit. You have to refer either this to the low voltage or the low voltage to the high voltage. This is very important. In the exam, you will see. Another important note, this is the last for the open circuit, is we said we are going to have meters at the low voltage, open circuit at the high voltage. In the exam, sometimes they change this one. They can put the meters whatever they want. As long as they included, they are giving you some notes or hints, you will know where exactly the meters are. Okay. So make sure that we follow whatever the examiners included in the question, even if it's against the normal, okay? Because they want to test your understanding. Short circuit. For the short circuit, it's similar to the open circuit actually, but you know, different in some way. When I put something short circuit, in reality, the current will be very, very high. So I'm not going to apply the rated voltage. I'm going to apply something much smaller than the rated voltage. And the current here, because it's a very, very high, I'm going to keep it or limit it to the rated current. This is the reason I'm not going to apply the rated voltage. If you apply the rated voltage and your transformer is short-circuited, the current will go very, very high. You are going to burn the windings of the transformer. So I'm going gradually increase the voltage until I reach it to the rated current, and that's it. Okay. So current is high, voltage is low. I'm going to go to put my meters at the high voltage, make the low voltage as a short circuit. Why I put the high voltage here? Because I don't want to burn my meters. So I'm going to put them at the one with a lower current. I know the high voltage is with a lower current, low voltage with high current. So I'm going to put the meters here up to reach to the rated current, which is low in general. Voltage applied at the short circuit is not the rated voltage. It's lower than the rated voltage. If you apply the rated voltage and you have short circuit, your current will be extremely high, and you are going to burn actually this transformer, or at least the windings of this transformer. As I said, we used to do this in the lab for the senior years. But with the short circuit, we usually have to be with them because it's more dangerous than the open circuit, right? It's if you go higher than the rated current, then you are going to burn your transformer. Okay. Okay, next we have the R and X equivalent. Let me first tell you why we have the R and X. Okay, for this current, we said the current will reach to the rated current, right? And this is the equivalent circuit for the transformer. You have the RC and XM or JXM. You can make sure that you include the J during your calculations. You have a short circuit here. As we said, the current will reach high, rated, up to the rated current. The current I note, as I said, it's a small current compared to the rated current. So you can ignore the entire branch. And your equivalent is just R equivalent and XM. Okay, sorry, X equivalent, sorry. It's referred to the high voltage, okay? You can always do this. It's referred to the high voltage. Okay, you can put J here. We have the same meters, P, short circuit, I, short circuit, V, short circuit, okay? PVI. Can I calculate the R equivalent and X equivalent? Yes. This time, they are in series. So I'm going to use them as impedance, which is much better, right? Impedance. How can I get the impedance if I have P, I, and V? Now it's a V over I. This is the magnitude. And the angle will be positive this time. Cosine inverse P over VI. Of course, you have to add the short circuit for, and this is the equivalent for every one of them. Okay. And of course, the V and I here are just magnitudes. Why the angle of this impedance is positive? You can, of course, you know, it's this is the reactance, right? And R plus JX for the inductance, right? This is one thing. So the angle must be positive. Or you can have, because you know the voltage reference as angle 0 and the current in this, and the current is, let's say the current with angle minus theta, and this is the current. If you divide this by this, remember, this angle will go up with positive sign. So it's a V over I, 0 minus theta, so it will be plus or positive, okay, with a positive sign. Then you get the real and imaginary of this. Real is the R equivalent, imaginary is the X equivalent. Refer to whatever in the exam. Let's say here it's high voltage, so make it high voltage. In the exam, it's low voltage. You follow whatever in the exam. We will see in the exam that sometimes they try to test your understanding. Okay. Let's go. This is just what we just said and explained. At the end, yeah, this is one note. At the end, you know, the R equivalent is the R at the primary plus A squared at the A of the secondary, X plus A squared of the X of the secondary. This is if it's referred to the primary, right, side. If it's referred to the secondary, you will find A squared here over A squared here, and there is no A squared here if it's referred to the secondary. So it depends. I usually use high voltage and low voltage instead of primary and secondary. Okay. Any question so far? This is how it looks like the problem for the transformer in the exam. So they provide this and asking you to solve getting the parameters. Do this short circuit test and the open circuit test. This is the S magnitude. This is the voltage. I believe this is 8,000, not 800. Okay. And do the open circuit test, short circuit test. This is what we have. In the open circuit test, what we said about the voltage, it's the rated voltage. This is the rated voltage. This is how I knew that there is a typo here. It's 8,000. In the short circuit, we reach to the rated current. Can we check this? How can I check? How can I get the rated current? I have the S and I have the voltage of each terminal or side. So I get the rated one, which is S over V as a magnitude, of course, V1, which is the 8,000. You can test it. The S is 20,000. If it's this, then the test is, as they said, on the primary or the high voltage side. In the exam, they don't say this one, but you can test, you can get I rated 1 and I rated 2 and check which one is the one they used. And this one, we will use 240. You can check which one is used for the short circuit test. You have the three parameters here, VI and P, VI, and this is P, sorry for the typo. Then you can do the tests, get the parameters. We are lucky because both at the primary, so once you have them, both at the high voltage, the here from this one, RC and XM, from this, it's R equivalent and X equivalent. Then we are good. You can draw them in one circuit. Any questions so far? This section is very, very small. Going to go through them quickly, and we are going to solve one of the exam problems to make sure that you understand. It's something called the VR, or voltage regulation. In the exam, after you get the parameters RC, XM, R equivalent, X equivalent, the four parameters, okay, and you have your circuit of the transformer, we call it the approximate equivalent circuit. Okay, RC, JXM, R equivalent. Let's say it's referred to the primary. Now, we want to know, to understand something called the voltage regulation. What is the voltage regulation? Let's say you have a transformer, the one they said like 8,000 to 240. We want to measure something called the VR. First, the V full load, the voltage of full load is one of these two. Let's say we are going to use the secondary one, the 240. So this one is the 240, 240. How can I calculate the no load? If this is the full load and it's given, you have to draw this circuit and They will provide something regarding the load. They will say, for example, the current is at full load and you are giving the S. So you divide your S by the voltage, you can get the current, and they will give you the power factor so you can get the angle here for the current. After you have the current, you multiply it by this reactance, okay, or this impedance, and then you get this voltage. This voltage actually is the no load voltage. Let me repeat this one. So you have this circuit. We know that this voltage at the load, we always assume, let's say it's the 240 angle 0, this one, or if you are in the primary, you are going to use this. I know the R, or we calculate it through the example during the exam. If they are giving the R equivalent and the X equivalent, we will put it. If they have the P short circuit and the I short circuit and the V short circuit, so I can calculate it. But can you calculate this current? Yes. This current will provide, they will give you in the exam, this is like full load or half load, for example. So you get I as a magnitude equals to the S over the voltage magnitude. You know the voltage because it's 240. S will be given in the problem. How can I get the current angle? Now I got the magnitude. The angle usually in the example or in the problem, they will tell you full load, and the power factor, let's say it's unity. So you know the angle is 0 for the current because it's the same angle as the voltage. If it's like 30 degrees, so 30 and the lagging, okay, so it will be 30 and there is a negative sign. If it's leading, so it will be positive. After you have the current, you can multiply this current times this reactant, this impedance, R plus J, plus this voltage, and you know this voltage. Very simple circuit. After you have this voltage, okay, you will use it for the no load voltage here as a magnitude. However, we don't understand now what is the voltage regulation. The voltage regulation is you have a transformer. When you put your load, you want the voltage to be, let's say, 240. Okay? If you remove your load, you will see the no load. In general, we don't like to have a very big difference at the voltage without the load and with the load. This is the voltage regulation. Because if you look at the circuit, so for this circuit, you measure this voltage, okay, with the load and without the load. With the load, it's the full load voltage, the 240. Without the load, this is what we calculate because no current will flow here. And with no load, this is the voltage here. It will be the voltage no load. So voltage no load to voltage full load as a percentage, this is what we call it the voltage regulation. If the voltage regulation is high, that this is something bad because it means there is a big difference between having the load with the load and without the load. If it's a smaller, then it's good enough. However, it depends also on the load itself. Let's write some, or let's draw some of the phasors. This is V2, the voltage here V2, and this is V1 over A. I referred it to the secondary, and this is something normal for the voltage regulation. You refer everything to the secondary. So this is RC over A squared. This is JXM over A squared. This is R equivalent, and this is X equivalent. By the way, if we are getting the voltage regulation at the, if your circuit is referred to the primary or the secondary, it doesn't matter. They will give you the same number. But here for this phasors, we used the refer to the secondary. So this is the angle, and as you can see, the angle is 0. This is the voltage, and the angle is 0. You have current here. You add this part, current times the resistance. This is the current. It's lagging. The resistance will be in phase with the current, the voltage across the resistance. Then you add the voltage across the reactance. It's 90 degree. The current is lagging, so this is 90 degree. Then this is the voltage. Okay. The magnitude, the difference between this magnitude, the no load, and the voltage at the full load, this is the voltage regulation. We call it positive because this magnitude is larger than this. Can we have a zero regulation? Yes, if they are both equal. Can you see that it happens when the current is leading? This is the current here. This is the angle. Current, then you put the part of the resistance and then the part of the reactance. Can we have negative regulation? Yes, when the magnitude is lower than this. You add this as a reference, add the one in phase with the current, then the voltage 90 degree on the current. If you put it here, it will be 90 degree auto. And then this is the one. If V2 and V1 over A in phase, yes, it may happen if you have this, it's lagging, of course, and this is the one parallel to this, then this one is 90 degree. And this is what we call it like the maximum regulation, when they are both at the same, aligned. Okay. I believe I can stop here for this module and solve, because I still remember next week you have to submit the assignment. So let me discuss the assignment number 3, question number 3, because now you can, I believe you have the things that, or like we already covered the things to solve this problem, or this problem 3 in the assignment. Okay. If you don't have any question, I'm going to give you some hints as I did with question 1 and 2 for the assignment. Okay, no question. I can continue here. So for this one, we have a single part. It's 2 parts, A and B. For this one, we have transformer. This is the frequency. And this is the voltage, primary or secondary, or high voltage and low voltage. Okay. And this is the S, magnitude, of course. And for this question, we provided the parameters R equivalent, L equivalent, not X, okay? How can we move from L to X? X equals to omega L, which is 2 pi times the frequency times L, okay? Don't forget the J with the L because it's imaginary. You have the RC and LM, which you can move it to XM using the same equation. They said they are all referred to the high voltage. So you can write down, it's all referred to the high voltage, all referred to the high voltage. If you want to draw them, draw in them in one of the circuit, it's referred to the high voltage. If you want to go to the low voltage, you have to multiply them by A squared or divided by A squared. So you have to use the referring. They ask it about the open circuit. What are the open circuit? Okay. And the short circuit. Rated voltage on the low voltage side. Short circuit rated current on the high voltage side. Volt, current, and power test results. So for this problem, they actually use the reverse. Instead of providing the test information and asking for the parameters, they provided the parameters asking for the test values, the P short circuit, I short circuit, V short circuit, P open circuit, I open circuit, and V open circuit. So how can we do this? We will use the reverse of the open circuit test and short circuit test. We actually have RC and we have JXM and we have R equivalent and X equivalent. We know that, for example, the voltage here at the open circuit is the V rated. They already provided this. And we know for the short circuit, the I short circuit is the I rated. So this is a good information. For example, here, what is the V rated? Let's first solve it at the high voltage, and then we can move it or refer it to the low voltage. So at the high voltage, I know that the voltage is 10K volt. We know RC and XM. Can I get the I open circuit? Yes. I naught or I open circuit equals to the voltage over the impedance. Voltage is this, impedance RC and XM in parallel. Can I get the P short circuit? Sorry, P open circuit? Yes, it's the voltage here, the voltage open circuit, the voltage rated, squared over the R. As we said, the power equal for the resistance or VI or I square R or V squared over R. If you have something, then because I have the voltage here, instead of trying to calculate this current, making current divider, I said, no, I can use this voltage. It's the voltage across the resistance and V square over R. This is the P open circuit. So I got actually the P, the V, and the I. Because here they are asking for the low voltage, then I'm going to move them one by one. Let's say the voltage will be the 230 volt. The current, you have to divide by A squared. By the way, the voltage reduced, so you will see that the current will be increased, right? This is what you expect. Voltage reduced, current increased. Power will be the same. At the low voltage or high voltage side, the power is not referred. The power in the secondary is the power in the primary. Similar we will do here. We know that the current is the short circuit, is the current rated. I can calculate this one actually because I have the S is given here. I have the voltage at the high voltage side, which is the 10,000. So this is 10,000. This is the S, which is 6600, right? Kilo or 6.6 kilovolt ampere. So you can calculate the rated current. After having this current, I can get the I square R to get the P short circuit, right? This is the I short circuit because the power here is the power losses at this resistance. So it's here. Can I get the V? Yes. Voltage is you can use actually the current, okay, times the R plus JX, right? This is the current, and I have the current R plus JX. Okay, and you can calculate the voltage. You can get the magnitude of the voltage by here, and this is the square root of R squared plus X squared. And you can get the angle because after you calculate the power here, you can get the angle by cosine inverse P over V over I. After you having the magnitude, you can calculate the angle. And definitely the voltage will be, let's say, the angle 0, but the current will be with the angle negative because R and here X is always lagging. It's always inductance here. Transformer is always included, like the equivalent circuit with the for the transformer is always with the inductance. Okay. I'm going to go through the step by step, but to solve the last one is straightforward. It's ideal transformer. So remember the transformer that we have, primary and secondary. The input voltage is given. There is no, this is ideal transformer, okay? Ideal, no, not like the equivalent circuit, no RX, X R equivalent or X equivalent, RC, XM. Okay, so you have this is the input voltage. The output current is 10 amps and voltage output is 120 volt. What is the input current? So V primary over V secondary equals to I secondary over I primary. So you have to reverse the current. So this one is 480. I primary, this is what we need. I secondary is 10 amp. V secondary is 120 volt. Can you calculate this? Yes. So I primary equals to 10 times 120 over 480 amps. That's it. I believe it's straightforward. Any question before we go through the solution? Okay, if there is no question, let me go very quickly because we passed the time. But it's here assignment number 1, problem number 3, point A, this is the giving and the equivalent circuit. I did it like as open circuit and short circuit. Okay, for the open circuit, I calculated the voltage, the current, then the power, V squared over R. The voltage, then I moved to the low voltage because this is what they asked it for. So I moved from the 10,000 to 230. The voltage reduced. So I expected the current from 40 milliamps to be increased to 1.739 amps. Short circuit, exactly the same. First, you know the current because you are in the rated. You get the magnitude of the voltage. It's I times the impedance. Then you can get the short circuit power. It's I squared R. So you have the ammeter, voltmeter, and wattmeter readings. Look at this. Remember the voltage at the short circuit, it's much lower the rated. Rated is 10,000, right? Look at this. It's not even a quarter of the rated voltage. Last one is, very simple. It's ideal transformer, primary and secondary. use the normal ideal equation or ratio between the primary voltage and current.
Yeah.
Oh, yes, please. We have a question. Any question? So no questions. We can finish here. We're almost done with the transformer. So yeah, I really wanted to finish it today, but we have maybe like very few slides regarding the per unit and the efficiency. That's it. Then we have a solved problem. Okay, so next time we will finish the transformer. This is the first thing we will do, and then we will continue to the DC machines. Any question before we end? Okay, thank you. Thanks so much, and see you next time.
Thank you.
Thank you so much.
Okay, bye.
Bye.